this video, we will introduce interaction terms in multiple linear regression. Now, so far, we've seen a model such as this, where we have two explanatory variables, for example, x1 and x2, and we are capturing the partial effect that x1 has on y by beta 1 and the partial effect that x2 has on y by beta 2. And even if we added quadratic terms to the model still has this potentially important restriction, which is saying that the partial effect of x1 never depends on x2 and vice versa. Okay. However, sometimes it's important or even natural to think about the partial effect of one variable, let's say education, to depend on the level of another variable, such as intelligence or experience or something else. Okay. And this is why we try to introduce interaction terms. So sometimes if our motivation or sometimes if our intuition tells us that interaction terms might make sense, we can actually test this out. So the way we introduce interaction terms is to just extend that same model that we had by introducing some sort of an interaction between x1 and x2. So we're basically multiplying x1 and x2, and then we're capturing the effect here, the effect of the interaction term by beta 3. Okay, now the important thing to notice is that since we talk about partial effects, if we want to talk about partial effects of x1 on y, this is now going to be different than before. So if you take the partial derivative of this equation with respect to x1, then you would get something like this. You would say this is holding everything else constant. This is just beta 1 plus beta 3 times x2, right? And now you can see clearly that the effect that x1 has on y clearly depends on the level of x2, okay? Unless beta 3 was 0, you're going to have this term, this entire term right here. And similarly, if we look at the partial effect of x2 on y, that is going to be equal to beta 2 plus beta 3 x1. Or in other words, that the effect that x2 has on y depends on the level of x1. So we are interested in basically testing whether beta 3, this coefficient that we have on the interaction term, is significantly different than 0 or not. So we can really just set up our hypothesis in this way. So our null basically says that beta 3 is equal to 0. And that is really the same as saying that the partial effects are constant, right? So if beta 3 was 0, notice in these expressions, if beta 3 was 0, you would just have beta 1 here and beta 2 here, right? And beta 1 and beta 2 are just constants. They don't depend on the level of another variable. Okay. So this is the hypothesis that we would like to test, and we can easily do that. Typically, if we cannot reject at a small significance level, it is not worth complicating the model by introducing interaction terms, okay? Now, what you want to do here is not get easily confused when we are working with interaction terms in our model. So when we are capturing the partial effect that x1 has on y and we come up with a term like this, we can easily see that beta 1 is the partial effect of x1 on y when x2 is equal to 0. However, x2 equal to 0 might not be true in your sample, okay? or at least not interesting when we are thinking about the population. Okay, so it's important to not try to interpret just beta 1 by itself. Sometimes we might want to evaluate or estimate the partial effects at the mean of the other variable. Okay, and so we can basically estimate something like this, where notice the effects are being captured at the mean of the other variable. x2 bar is representing the mean of x2, and similarly x1 bar is capturing the mean of x1. Okay, so these are just sample averages that you draw from your sample. And typically to obtain those, the effects, the partial effects, delta 1 and delta 2, we can change our model in this way, where we are taking or demeaning x1 and x2 before thinking about the interaction term. So earlier we just had x1 times x2 next to beta 3, but now we have demeaned, in this case, demeaned the variables before interacting them. Okay. So here's an example. For instance, if we were interested in understanding, do education and IQ have an interactive effect in the log wage equation, we might be interested in having on the left hand side log wages and on the right hand side education, IQ, and then an interaction term, education times IQ. And so the first step would be just to estimate the model where the interaction is just education times IQ, where the means haven't been removed from before creating the interaction. And the second type of regression that you could run is with something like this: beta 3 times education minus the mean of education times IQ minus the mean of IQ. Okay, so here from the data set wage 2, I have already calculated the means. So let's take a look at that first regression. So let's say we get something like this. When we ran our first regression without demeaning the interaction term. In this case, I'm not showing you the results here, but just believe me for now that the p-value is 0.4 or 4%. Okay, so this is for the interaction term. And so if that's the case, then we would reject the fact that the interaction term has no effect on log wages. So here we can take a look at what these coefficients actually mean. So if we look at the coefficient on education, this is telling us that if what is the return to education for someone with IQ equal to 0, because we're holding everything else fixed, okay? And the IQ coefficient is the effect at education equal to 0, okay? Because remember, the effects are captured here. The effects are captured if you look at what is the partial derivative of log wage with respect to education, that is going to be equal to the beta hat for education plus beta 3 hat times IQ, right? So if we just want to interpret beta hat education, that is just saying what is beta hat when IQ is 0, okay? Or what is the effect when IQ is 0? Okay, and now what happens? Let's see what happens when we introduce, when we have centered the interaction term. So in this case, I've not written it correctly here, But this is basically when you've subtracted off the means. So the mean of education has been removed, and again, maybe we'll just write it the way we wrote it before, education bar, okay? So this is what it is. And here, when we estimate the model, we find that the coefficient on education drops significantly. And the idea here is that, or the interpretation here is that at average levels of education, the return to education is about 7.8%. So if IQ is at the average, right, then this term would disappear, and the partial effect of log wage with respect to education is going to be 0.077 minus 0.0011 times IQ minus IQ bar, right? So this will just disappear if IQ was at that mean, okay? And so we're saying that this is just 7.8%, okay? Okay, and here the negative coefficient on the interaction basically means that the return to education is higher for people with low ability. Now we can also see what happens when we look at this effect, this partial effect, when IQ is, say, 10 points above its mean value, okay? So here we're basically multiplying 0.0012 with 10, right? So if IQ was greater than 100 by 10 points, then we're just capturing that effect here. And we are saying that the return to education is going to be 6.6%. However, for someone who had an IQ which was 10 points below the mean, the return is going to be this, right? So if this is below the mean, which is to say that if this is 90, this entire expression turns negative, and then therefore you have a positive sign here, okay? So the return to education in that example is going to be 9%. Okay, so here we can see that schooling is worth more for those with lower intelligence, for instance.